So AI has gotten really popular as of late, especially large language models like ChatGPT and more recently Google's Bard. And maybe you've considered breaking into the field and learning it for yourself. Well, much like anything in tech, it's important to start off with the basics. Some kind of, as they're most often called, Hello World program is an important first step. That's what we aim to set up in this video here. Keep in mind, this model will be very simple and relatively dumb, but the same can be said about printing 2 words to a screen to make sure that you have a basic understanding of a new language. In order to actually get this model set up, we're going to need a couple of prerequisites, those being CUDA, CUDNN, and TensorFlow, and a few Python packages. But if you don't have CUDA and CUDNN installed, got a little shameless plug here for a video that I made recently on getting those squared away, so you can check that out and come back to this one. Furthermore, this will be an overview using the high-level machine learning libraries available in Python. If you've never worked with machine learning, I recommend looking into getting a simple model set up in C++ or researching how the math behind these models works. But I'll go over all of this in another video, so stay tuned. Alright, now let's actually get started with the code. Now for this tutorial I'm going to be using a Jupyter notebook to kind of simplify and go step by step what each individual block of code is doing. If you don't know what a Jupyter notebook is, they're basically Python files that are split up into sort of a notebook format where you can render a markdown, you can render images right here in the IDE, and it's a commonly used tool for machine learning devs and data scientists. So first and foremost, we import NumPy and matplotlib for numerical operations and data visualization. TensorFlow is our main library for building and training the machine learning model. Load.img from keras preprocessing.image is used to load the images, while visual keras is used to visualize our model's architecture. bil.image is used for image processing, and finally, TensorFlow datasets is used to load our dataset. Alright, so now we're just going to run this block of code here, make sure that everything imports correctly. And if it works, you should see some kind of TensorFlow message here. Now we're going to run another block of code here just for peace of mind and to ensure that we have our environment set up correctly. We're going to print our TensorFlow version, and we're also going to print the number of GPUs that we have available with this line here. I'm going to run that, and you should see something like this. So our TensorFlow version as of right now is 2.11.0, and our number of GPUs available is 1. I only have 1 in this machine. Alright, so now we're going to define a basic draw function. This is going to let us get some visualization on the handwritten digits that we're actually passing into the network here. Pretty basic. All it does is take in the raw data for the handwritten digit as this variable in here, and then it will use matplotlib to create a plot for our image, and then we just show that plot. So, like I said, this won't be used until a little bit later down the line, but good to define it here. Here, we're loading in the MNIST dataset via TensorFlow keras datasets MNIST. The MNIST dataset is a collection of 70,000 grayscale handwritten images. And then here, we will declare the dataset, load it in, and then we split it into training sets and testing sets. Pretty important concept for machine learning. Whenever you're creating your model, you want a significant portion of the dataset to be used for training and a small portion of it to be used for testing. You can validate how well your model is built. Now we're going to use that draw function that we set up earlier to take a look at the first item in our training set, which just so happens to be this lovely 5 right here. And yeah, this is really just for visualization purposes. Now we're going to actually start defining the architecture of our machine learning model. This is a sequential model with 3 layers. The first is a flatten layer, which will reshape our 28 by 28 pixel images into a 1D array of 784 pixels. This is necessary because our dense layers expect 1 dimension of input. The next 2 layers are dense layers with 128 neurons each using the ReLU activation function. ReLU is a common choice for hidden layers in a neural network. Finally, we have our output layer here, which is our dense layer. And as you can see, there are 10 neurons in this network. Each of these neurons represent 1 possible state for the handwritten digit. Because these digits go from 0 to 9, there are 10 total possibilities that it could be, thus 10 neurons. Now I'll explain activation functions for those of you who are unfamiliar. The way that a neuron effectively works is it takes in a sum of values, one value, sum of many values, but it processes them all into one cohesive number that the neuron processes. And that number is usually between 0 and 1, or in some cases, -1 to 1. And the activation function is essentially a function that, well, activates the neuron. What does it mean for a neuron to be activated? Well, if a neuron is activated, it puts out an output signal of 1. If a neuron is not activated, it puts out an output signal of 0. And that output signal is then processed by other neurons in the network. So the ReLU function is just one of many different activation functions. With some tinkering, I found that the ReLU is the best activation function for this specific model, but not every model. Every model is different, and you may require other activation functions like leaky ReLU, tanh, sigmoid. There's quite a few. Now let's actually build our model here. Code. As you can see, no errors here, so we were able to build our model. Now just to work some more visualization in here, we can use visual keras to actually visualize what our model is doing. So here we have our input flatten layer there, and then our two dense layers, and then our output dense layer. Now it's time to actually compile and train our model. We need to set our optimizer, the loss function, and the metrics that we want the model to track. In this case, we're building a classifier, so accuracy is a good metric to track. The Atom Optimizer is a relatively popular choice because it will automatically adjust the learning rate during the training. The sparse categorical cross-entropy loss function is used for multi-class classification tasks. We'll also be tracking accuracy, as mentioned before, as our performance metric, as we're building a classifier, not a regressor, so accuracy is a good metric to track. That's the actual compilation of our model here. This model.fit call is when we actually train the model. Essentially, it will run through one training session at a time using the xtrain dataset and the ytrain. Essentially, it will run through one iteration of the model, also known as forward propagation and then back propagation, using the x-training set as input and the y-training set as an output validation. And we're going to be running it for 10 epochs. An epoch is essentially one step through the model. So one forward prop and one back prop. We're going to be doing that 10 times. So let's train our model here. And as you can see, as the model trains, our accuracy value goes up and our loss value goes down. Very simple overview of this. Loss is essentially a measure of the lack of performance of the model, and accuracy is pretty self-explanatory. How accurate is the model? You can see we're getting about 99% accuracy with this data set. Now we're going to get a summary of our model here. So by running this, it will tell us some more information about our model. The sequential model, these are the layers and the various types. So our flattened layer, our dense layer, our first dense layer, our second dense layer, and our output dense layer. You can see here it has 118,000 total parameters and 118,200 trainable parameters. Now we're going to get some more statistics about our model here, and these are just the final loss and final accuracy values of our model. Dump that out here. You can see we got a loss of 0.103 and an accuracy of 97%. With a little bit more training, we could get this number down and this number up, but these are acceptable statistics for this current model. Now we get to the fun part. We're ready to make predictions. We used our trained model to predict the class of the images in our test set. Here, we're going to grab all of the predictions from our test set here. We're going to label them with the Y test set. We're going to print our predictions. Specifically, we're going to print our predictions at space 2 here, and that's because in our label we chose the second index. And then we're also going to draw the image so we can compare what the model predicts with what the actual image looks like. Go ahead and do that right here. You can see the model predicted 1, and the label here, which is the actual value of the image being passed in, is 1. So this was correct. And we can see here, this is the actual image that it was given to make that prediction, and that certainly looks like a 1 to me. Alright, now we get to put our model truly to the test here by passing in data that it has never seen before, and seeing if it can make accurate predictions based off this data. So, the data that I'm going to be passing it is a digit that I drew myself. Here I just drew a 28 by 28 image of a 7. And that's this file here. But in order to actually pass it into our model, we can't just pass it in raw. We need to do some reformatting. So we're going to resize it to 28 by 28, even though it could be that already. It's good to double check. Then we convert it to grayscale, invert the colors here, and then we reshape it again just to make sure that there was no... Then we reshape it again to 28 by 28. Then we print our image shape, and then we will display the image shape as well here. We'll go ahead and run this, and there we go. We got the right shape here, 28 by 28. That looks a whole lot like this image we passed in over here. So it looks like it is loading correctly. So now all we have to do is pass this image file into our model, save what it predicts into these predictions variable here, and then we're going to print out the prediction with the highest probability. As our model makes multiple predictions, it predicts the probability of this number being any of the possible numbers, but we're just going to choose the one with the highest probability because that's what the model assumes the number is. Let's go ahead and run this. And you can see the model guesses that we have a 7 here. And lo and behold, it seems to be right. Now for our last step here, we can save our model to a .h5 file. This is the file that Keras will use to essentially load in the model in the future. So if we like the model here, we think that we've trained it well, we built a good model, we can go ahead and run this. And there we go. We have num classifier.h5. Now this model can be loaded into another script or another program, and we can use our digit classifier model without having to train it every time. Train it once and then pass in this file somewhere else, and we have a functional model. So that's the end of this video. We built a digit classifier using TensorFlow, and it can now recognize handwritten digits. Like I said, this is a very basic example. This is kind of the hello world of neural networks, I would say. I plan on doing a lot more of these types of tutorials in the future, so if you're interested in seeing that,